Hi students, welcome to Lakshya Academy YouTube channel. We are in the concept of transistors. This concept is very important for both JEE and NEET, and you can expect 90% question from this concept. In last video, we completed common base configuration of a transistor, common emitter configuration of a transistor, and common collector configuration of a transistor. And today I will explain characteristics of a transistor. Okay, so before going to that concept, I brief some of the concepts. We have two types of transistors, Npn transistor and Pnp transistor, and a transistor has three terminals. Those terminals named as emitter, base and collector. Emitter is heavily doped, base is lightly doped, and collector is moderately doped. And the base is very thin, width of the base is very small, and emitter is slightly less than that of collector region. So in NPN transistor, base is p-type semiconductor and emitter and collector are n-type semiconductors. Working of an NPN transistor. The emitter base is connected in forward bias condition and base collector junction is in reverse bias condition, and emitter is heavily doped. So in this region there is availability of majority charge carriers. So this is n-type semiconductor, so majority charge carriers are electrons. So these electrons are repelled by the negative terminal of this battery and they move to the base region, but base is lightly doped, so only 5% of about 5% of electrons only combine with holes, and the remaining about 95% of electrons jump into the base, move to that collector region. This is so that's why this region is named as collector. It collects charges, and about 95% of electrons which enter into the collector region are attracted by the positive terminal of battery, VCB. And in the case of NPN transistor, the direction of conventional current is from base to emitter. The action of Pnp transistor, working of Pnp transistor. So in Pnp transistor, the emitter is p-type semiconductor and base is n-type semiconductor, and so emitter base junction is forward bias and base collector junction is in reverse bias. So The majority charge carriers in emitter region are holes. These holes are repelled by the positive terminal of the battery and they enter into the base region, and very few, about 5% of electrons available in the base region combine with the holes. The remaining holes move to that collector region, and those holes are attracted by the negative terminal of the battery. And in the case of Pnp transistor, the direction of conventional current is from emitter to base. So in majority charge carriers are holes in Pnp transistor. Okay, this is the working of Npn transistor and Pnp transistor, and in a transistor there are two PN junctions. Come to that new topic, characteristics of a transistor. Transistor characteristics are the nothing but the plots or graph represents the relationship between current and voltages. So we can define the transistor characteristics in CB mode or CE mode or CC mode. Okay, transistor characteristics are the graphs between the current and voltages, and there are input characteristics of a transistor and output characteristics of a transistor and current transfer characteristics. And particularly the input characteristics of a transistor in any mode. Any mode means CB mode or CE mode or CC mode. The input characteristics of a transistor observes changes in the input current with the variation in the values of input voltage. So while studying the input characteristics of a transistor, the output voltage kept constant. So by arranging the output voltage kept constant and the relation between the input current and input voltage are the input characteristics of a transistor. And next one, the output characteristics of a transistor is nothing but a plot between a graph between output current and output voltage when input current kept at constant. So to study the output characteristics of a transistor in any mode, the input current should be maintained at constant. So output characteristics of a transistor is nothing but a graph between output current and output voltage. So the output characteristics of a transistor should be observed when the input current kept constant. Next, third one, the current transfer characteristics. This characteristic curve shows the variation of output current with the input current when output voltage kept constant. So when output voltage kept constant, the relation between the changes of input current with the output current gives the current transfer characteristics of a transistor. Okay, So to observe the input characteristics of a transistor, the output voltage should be kept constant. To observe the output characteristics of a transistor, the input current should be constant. And to observe the current transfer characteristics, the output voltage kept constant. The input characteristics are the relation between input current and input voltage, and output characteristics are the graph between output current and output voltage, and current transfer characteristics are the graph between or variation of output current with input current. Yeah, consider Pnp transistor in common base configuration. Consider a Pnp transistor in a common base configuration. A Pnp transistor, the direction of conventional current is from emitter to base, and n-type semiconductor is base in Pnp transistor, and it is connected to an external circuit. And I explain each and every part of the circuit. This is the Pnp transistor, and we consider in common base configuration. So base is common to both input and output. So input is measured across emitter and base, and output is measured across collector and base. IE represents the emitter current, IB represents the base current, and IC represents the collector current. So to measure the current, the instrument that can be used to measure the current in electrical circuit is ammeter. So this is milliammeter, and ammeter is connected in series in the external circuits. So in this ammeter we can measure IE value, emitter current. This is the positive terminal of the ammeter, and this is negative terminal of the ammeter, and ammeter is connected like this. This is negative terminal connected to emitter. So using ammeter we can measure IE value. And the voltage across emitter and base is VEB. The instrument which can be used to measure the voltage is called voltmeter. So this is the voltmeter, positive terminal of the voltmeter and negative terminal of the voltmeter. In external circuit, voltmeter should be connected parallel. So this is parallel to these emitter and base. So in this voltmeter it records VEB value, voltage across emitter and base. And this p-type semiconductor is connected to, just observe, to positive terminal of the battery. P-type semiconductor is connected to positive terminal of the battery, so it is in forward bias condition. Emitter base is in forward bias condition, and this is the battery, and this is rheostat. The purpose of rheostat is we can change the resistance value. If we change the resistance value, and there is a change in the current. Okay, so the purpose of rheostat is to change the values. So the input parameters are IE and VEB. IE can be recorded in a milliammeter, and VEB can be recorded in voltmeter. Using this rheostat, we can change the values by changing the resistance, and we can change the values of VEB. So we observe, if we change the value of VEB, how the value of IE changes. And this is the output circuit, and output current IC can be measured using the second ammeter available in the circuit. P-type semiconductor is connected to positive terminal of the ammeter, and this is negative terminal of the ammeter. And the output voltage VCB can be measured by using the second voltmeter available in the circuit. So this is a variable resistance, so we can change the value of VCB. Okay, the Pnp transistor in a common base configuration mode. Yeah, to observe the input characteristics of a transistor, the output voltage should kept constant. VCB should kept constant, and by changing the values VEB, we have noted the values of IE in the milliammeter. So first we observe the input characteristics of the transistor. So input characteristics, to observe the input characteristics of a transistor, a graph is plotted between VEB and IE, and while plotting the graph, VEB is taken along x-axis, independent quantity, and dependent quantity should be taken along y-axis. Yeah, in the first case, when VCB, voltage across collector and base, is kept at 0 volt, and the voltage between emitter and base gradually increases from 0 to 1 volt, and that range depends on the type of the transistor. Okay, so this in this first line, VCB is maintained at 0 volt. When output voltage VCB maintained constant, by changing the value of VCB and the values of IE recorded and tabulated, and a graph is drawn between VEB and IE. It is a curve. From the graph it is observed that and when VEB equal to 0, IE value is also 0. even though if we increase VEB value, that means 0.1 volt or 0.05 volt, and IE is also 0, and when VEB is gradually increases 0.2 volt like that. So if VEB, I am mentioning that VEB is increasing in the order of 0.1 volt, or you can change in the order of 0.05 volt also, and IE also 0 at a particular point, and at a particular voltage, of VEB, and there is current observed in the ammeter, that means IE is observed, and after that, even though for small change in VEB after that region, and current in the emitter changes rapidly. Why? What is the reason of this? And to know the reason of this, already you know that PN junction diode depletion layer, potential barrier. The barrier potential for silicon is 0.7 volt, and for germanium it is about 0.3 volt. Already you know that. We discussed in PN junction diode part. When p-type semiconductor and n-type semiconductor are suitably joined, PN junction diode can be formed. So there is diffusion of charge carriers from one region to another region. So at the junction potential barrier depletion layer can be formed. So the potential difference across the depletion layer is potential barrier. So for silicon, the barrier potential is about 0.7 volt, and for germanium it is about 0.3 volt. So if we consider the silicon, and if the applied voltage is less than that of 0.7 volt, and charge carriers cannot cross the depletion layer, so there is no meaning of current. So when the applied voltage is equal to or just above the 0.7 volt in the case of silicon, so there is chance of moving of charge carriers from one side to another side. Current is nothing but flow of charge carriers. So if the applied potential is greater than that of that barrier potential value, there will be current. So that is the reason. Okay, so from 0 to the certain value of VEB, that certain value depends on the type silicon crystal or germanium crystal. So this is the reason for that. Why, even though if we change VEB value to a certain value, we do not observe IE value also 0, and if the applied voltage is greater than that of the barrier potential, then we observe the current, emitter current. Okay, the same procedure is repeated with a constant of 10 volt of VCB. So after that, the voltage across collector and base is maintained at minus 10 volt, and again VEB first kept at 0 and slowly gradually increases in the same order, and the readings of IE in the ammeter are registered, and readings are tabulated, and graph is drawn between VEB and IE, and the graph is a curve. This is the second line. So actually you can observe that the input characteristics can be changes when VCB value changes. And in the third case, when VCB is maintained at minus 20 volt and the same procedure is repeated, that means the value of VEB changes in a proper order, and the values of IE is calculated and noted in the milliammeter, and they are tabulated and graph, and this third curve represents that graph. So for different values of VCB, we observe the change in input current for the changes in input voltage VEB. These are nothing but input characteristics of a transistor, and a graph is drawn between VEB and IE. It is a curve, and up to a certain limit and current in the emitter is 0. So after the certain limit, the current increases very rapidly. So the input characteristics of a transistor can be observed when the output voltage is kept constant. Keep it in mind. Okay. And next, the output characteristics of a transistor, Pnp transistor in common base configuration. So already I mentioned that to observe the output characteristics of a transistor, we have to maintain the input current kept constant. Input current kept constant. Okay. So output characteristics of a transistor is nothing but a plot or graph between output voltage VCB and IC. VCB and IC. So this is observed when IE is kept constant. So I have chosen three different cases. In the first case, I chosen IE is equal to 0 milliampere. Okay, 0 milliampere. And by maintaining the IE value kept constant and VCB, the VCB values changes, and if VCB changes and the current IC, collector current, is measured in a meter, and they are tabulated, and the values of VCB changes in a proper order, and the readings are tabulated, and a graph is drawn between VCB and IC, and it is a curve like this. So at this negative potential, negative value of VCB, and the current in the collector increases slowly. And in the second case, when IE is kept at 10 milliampere, the same procedure is repeated, and for the different values of VCB, the different values of IC can be noted, and the graph like this. Students, observe that when IE value changes, and the minimum value, that means at a particular value of VCB, IC value starts and that is changes. If we increase the value, and it shifts to the left side. And in the third case, when IE is maintained at 20 milliampere, and for different values of VCB, and different values of IC can be measured, and the graph look like this. So these are the output characteristics of a transistor. So initially I explained the PNP transistor characteristics in common base configuration, and input characteristics and output characteristics. And next, PNP transistor characteristics in common emitter configuration. Procedure is same. And this is common emitter configuration. So emitter is common to both input and output. IE is emitter current, IB is base current, IC is collector current. So this is the input circuit and output circuit. To read the input characteristics of a transistor, we have to maintain VCE a fixed value. So ammeter and voltmeter. In ammeter we can measure the current. The device which can be used to measure the electric current is nothing but ammeter, and the device which can be measured potential difference is nothing but voltmeter. Input characteristics of a PNP transistor. VBE is input voltage and IB is input current. Okay, the input characteristics of a PNP transistor in common emitter configuration. When VCE is kept constant, VCE kept constant, the graph looks like this. For different values of output voltage 0 volt, 0.1 volt and 0.2 volt, with the change of VBE we can measure the IB values, and this represents curve. And the output characteristics of a PNP transistor in common emitter configuration. Common emitter configuration is so graph between output voltage VCE and output current IC when IB is kept constant. Output characteristics of a transistor. Output characteristics of a transistor, we observe the changes in output current and output voltage when input current kept constant. And next, I consider NPN transistor in common emitter configuration only. Okay, so this is NPN transistor. In NPN transistor, P-type semiconductor is base. The direction of conventional current is from base to emitter. So in common emitter configuration, and emitter is grounded, So IB is input current, VBE is input voltage, and IC is output current, VCE is output voltage. And this represents variable battery. In the previous I consider the rheostat diagram. Here I mentioned the variable battery. That means we can change the values. Yeah, the input characteristics of NPN transistor in common emitter configuration. Input characteristics are nothing but graph between VBE and IB at constant VCE. The output voltage VCE is fixed, whatever may be 0 volts or 0.10 volts or 20 volts, like that. The input voltage is changed in small steps. For example, 0.05 volt or 0.1 volt up to 1 volt, and the corresponding base current is noted, and graph is drawn between VBE and IB. In the case of NPN transistor, the input voltage is VBE, input current is IB, and VCE is output voltage. VCE is kept constant, and this graph represents for 10 volt, this graph represents for 20 volts. Okay, so at a certain value of VBE, the IB value observed. After that, by small change in VBE, and the IB value changes rapidly. So the input characteristics of a transistor is nothing but the plot between VBE and IB, plot between input voltage and input current, by keeping output voltage constant. Yeah, from the input characteristics, from the graph, we can calculate the input resistance of a transistor. Already you know that the input resistance of a transistor is the ratio of change in base emitter potential to the change in base current when VCE is kept constant. So from the input characteristics, we can calculate the input resistance of the transistor. And the output characteristics of CE configuration of a transistor, the output characteristics are nothing but collector characteristics. This is the graph between IC and VCE when IB is kept constant. And from the output characteristics graph, we can calculate output resistance of a transistor. Output resistance of a transistor is the ratio of change in voltage across collector emitter to the change in collector current. Okay, the output characteristics of NPN transistor in common emitter configuration. So if we observe the output characteristics of a transistor, actually this is important, and for IB 10 microampere value, the graph is when IB value changes, the maximum value of IC also changes. This is the maximum value of IC. And if IB value increases, here I mention 6 different values of IB: 10 microampere, 20 microampere, 30, 40, 50 and 60 microampere. So from the graph, it is very clear to you that if IB value increases, the saturation value of the maximum value of IC also increases. So from the graph, I mentioned three different regions, and this is one of the region. Observe carefully. And this is another region, saturation region. And the third part is this region, red part, active region. Cutoff region, saturation region, and active region. From the output characteristics of a transistor, from the output characteristics graph, so I mentioned three different regions: cutoff region, saturation region, active region. So next I discuss when a transistor is in cutoff region, when a transistor is in saturation region, when a transistor is in active region. Yeah, first one I focus on saturation region. Yeah, this is the saturation region of a transistor. Yeah, from this graph, yeah, just analyze the graph. In this region, the collector current almost independent of the base current. Collector current is almost independent of base current. So in the saturation region, the collector current is almost independent of base current. This happens when both the junctions are in forward bias condition. And what is the advantage of saturation region that I discuss later. So in this region, the collector current is independent of, almost independent of base current. So this happens when both the junctions are in forward bias condition. So saturation region is possible when both the junctions are in forward bias condition. Next we move on to that second region, cutoff region. This is the cutoff region. When IB is at 0, so here I consider 7 different values from 0 to 60. So this is very close to that x-axis. So if a graph is very close to that x-axis, it means that the y value is very close to 0. So in this region, the y component, that means the collector current is almost 0, very close to 0 in this region. With this arrow I mentioned that cutoff region. So this happens when both the junctions are in reverse bias condition. So cutoff region, in cutoff region the value of IC is almost 0, very close to 0. This happens when both the junctions are in reverse bias condition. Next we move on to that third region, active region or linear region. So here the base current is in microampere and collector current is in milliampere. So collector current is more than that of base current. In this region, the collector current is far greater than, many times greater than that of the base current. Even though a small change in input current produces a large change in the output current. Okay, a small change in the input current means IB value. A small change in input current, we observe a large change, a great change is observed in output current, that is collector current. So this is possible when emitter junction is in forward bias condition and collector junction is in reverse bias condition. So active region is possible when emitter junction is in forward bias condition and collector junction is in reverse bias condition. So in this region, for the small change in the input value of current, there is a large change observed in the output current, that is IC, collector current. Okay, saturation region, cutoff region and active region. In saturation region, both the junctions are in forward biased condition, and in cutoff region, both the junctions are in reverse bias condition. In active region or linear region, emitter junction is in forward bias condition and collector junction is in reverse bias condition. Yeah, a transistor can be used as amplifier or a transistor can be used as an electronic switch. Transistor cannot be used as a rectifier. A transistor can be used as amplifier. In the next video, I explain how a transistor can be used as an amplifier. And a transistor can be used as an electronic switch also. So the transistor works as an amplifier when it is operated in active region. This is very important concept. The transistor works as an amplifier when operated in the active region. So for the external circuits, for the logic gates, whatever may be in electronic devices, if we want to use the transistor as an amplifier, so that transistor should be operated in active region only. So when the transistor is used in the cutoff region or saturation states, it acts as an electronic switch, on or off electronic switch. So when the transistor is used in the cutoff region or saturation state, the transistor can be used as an electronic switch. Okay, so a transistor can be used as an amplifier and a transistor can be used as an electronic switch. So we have the transistor as an amplifier in our syllabus. In the next video, I explain that. The concept of transistor is very important and very easy, students. So you can easily understand the concept of transistors, and for the entrance examinations, JEE or NEET, you can expect one question from this concept. Okay, thank you.